Welcome to your first lesson in Chapter 5 on momentum and impulse. When we talk about linear momentum given by P, and I will just refer to linear momentum from now on just as momentum, we are talking about a quantity that describes the motion of an object traveling in a straight line. And you can tell right now that we do refer to momentum as a vector quantity. And when we're talking about describing the motion of an object traveling in a straight line, momentum is merely defined as a product of its mass and its velocity. And momentum is measured in kilogram meters per second, which if we do a little bit of a unit analysis kind of makes sense due to the fact that mass is measured in kilograms and our velocity is measured in meters per second. Momentum, kilogram meters per second. That is our equation and unit when we calculate or do momentum style problems. And let us start with a simple example first. We are going to calculate the momentum of a 4.1 times 10 to the 5 kilogram jet traveling north at 658 kilometers per hour. Quite a simple question in this case because we are given both the mass we're going to let north also, before I continue any farther, be positive. And we are given a velocity of 658 kilometers per hour. And it's pretty obvious that we need to first convert that to meters per second. So we divide by 3.6 to do that conversion. And that is 182.7778 meters per second. Let us calculate the momentum of this jet. So that will be 4.1 times 10 to the 5 multiplied with 182.7778 gives us 74,938,980. From this question, I need only two significant digits, so that will be 75 million kilogram meters per second. If you want to convert this into scientific notation, it is more than welcome. It's a little bit easier sometimes to possibly read scientific notation. In this case, that would be 7.5 times 10 to the 7 kilogram meters per second. And both of those questions or answers are acceptable. When we talk about linear momentum, we must also talk briefly about impulse. Impulse being represented by F delta t. And this is the product of force and time that acts on an object to change its momentum. Mathematically, when we talk about impulse, F delta t, which is our impulse, is equal to our change in momentum. F delta t is our impulse. F is our applied force. T is our time in seconds. Force, of course, in newtons. And delta P is our change in momentum. And our change in momentum is given in the unit Newton seconds. Again, coming from the fact that impulse is F delta T, Newton seconds. Let's look at this delta P for 1 second. Delta P is our change in impulse. And remember that impulse is merely mv. So therefore, this would be mvf minus mvi. Factoring, that tells us that it's mvf minus vi. So therefore, that would be m delta v, change in velocity. So when we think about our impulse, F delta t, that is the same as m delta v. And this m delta v change in velocity is merely our acceleration. So this is an extension on Newton's second law that we see in this case. So let's look very quickly at an impulse problem or question that might arise. Anybody who plays billiards here will appreciate this example. A billiard ball that has a mass of 200 grams rolls toward the right-hand cushion at 2.0 meters per second, and then rebounds straight back at 2.0 meters per second. For this problem, what we shall do is we shall set the direction of right as the positive direction. And we will see in this case that our final velocity, Vf, is equal to negative 2.0 meters per second as it's rebounding back towards where it came from, so to the left. And Vi in this case, going to the right, is also going to be 2.0 meters per second. We're going to calculate in part A the impulse that's given to the ball by the cushion. So we are going to calculate F delta t. So F delta t, our impulse, will be equal to m Vf minus Vi. So therefore, F delta t will be equal to our mass, which will be 0.200, multiplied with negative 2.0 minus 2. So this is going to be 0.200 multiplied with negative 4.0, or negative 0.200. 0.8. So therefore, F delta t, our impulse that's given to the ball, is negative 0.8. And let us check for units quickly as well, which are Newton seconds. So let us look at part B. If the ball is in contact with the cushion for 0.25 seconds, how can we figure out what force was actually applied to the ball? So this tells us, and by the way, my impulse, the change in momentum, this will be in the direction of left. So we will change that back into a positive. Our answer was negative. Let's actually include the direction as well. Let's figure out what force was applied. We know that the impulse F delta t was negative 0.8 Newton seconds. And we also are given in this case that the time is 0.25 seconds. Let us calculate F. Well, this is merely a matter of the fact that my impulse is given by F delta t. And since impulse is the same as my change in momentum, we can say that the force will be equal to that changed momentum over that time. So that is negative 0.8 all over 0.025. And this will help us to solve for what our force that was applied to the ball, in this case by the cushion. Which, when we do the division, we see that we get an answer of 32. And let me scratch that out for 2 seconds. Negative 0.8 divided by 0.25, because there's 25 seconds that I gave you in the question, which is 3.2. One significant digit tells us that in this case, the force applied to the ball by the cushion would be 3 newtons left. My initial example had the 0.025. I changed it in this case to 0.25. That's where my mistake initially came from.